So how do we resolve this? One would be removing the conflicting facts. So the example in the book is, suppose that you had a very high level system and it had both a stop and a go action to be fired off. So because of your rules and because of your current working state, you got both a go and a stop action. You could create a rule that says basically if you have both stop and go, stop, therefore just remove the one that doesn't make sense, thus removing the conflict. The other way of doing it would be preventing the addition of the conflicting fact in the first place. So, they give the example of stopping if a pedestrian is in the walkway. Well, you should add a rule that if if you're trying to go and there's a pedestrian in the walkway, then stop. That way, if you're already stopped, you don't have to worry about it. If you have the go action as well already queued up, this will just take care of it and remove it. And the last thing you can do is have a rule priority, so that suppose you had both a go and a stop, you could just make one a higher priority. In this case, the logical thing would be to stop as the higher priority, because it's better to not do anything than potentially run somebody over. So let's look at two different ways that you can actually use the inference engine. So one is the forward chaining inference, and this is kind of what I mentioned before, where you have your known facts, you apply it to your current rule set, you get the next fact, or what we call the action, find out if there's any more rules based on all your other current facts, keep going on, chaining one to the next to the next to the next. So in this case, the red light is flashing, we got a rule that if the red light is flashing, caution is required, so we add caution is required to our current working set. We also know that the vehicle is moving, so now we have caution is required, vehicle is moving. There's another rule that says caution is required and the vehicle is moving, you should stop. So we stop. It's pretty simple. And so the advantage of this is you can see exactly what actions are required to get to your final state. The other way of doing inference is a backwards chaining. So this is, given a specific outcome, the final action, what pieces in our working set, what facts would we have to have in our working set in order to achieve that? So let's suppose we think we need to stop. We can say, okay, what are all the rules that possibly cause us to stop? One is, if caution is required and vehicle is moving, then stop. If we know that the vehicle is moving, then the only other fact we would need is that caution is required. And we can also go back further and find out what other rules would cause that to be true. In this case, if the red light is flashing, then caution is required. So we now know that if the user of the system thinks they have to stop, the only other thing that they need to know is whether or not the red light is flashing. So the system could come back to the user and say, is the red light flashing? If that's true, then we know immediately we have to stop. Now this isn't really useful in games per se, but it's very useful in medicine, where you want to eliminate all the possible different outcomes that couldn't possibly be based off your current working knowledge. So there's many different illnesses out there. If you know the patient has a fever and half of them off the bat don't have that as a symptom, you eliminate them all already. You keep going through all the other facts that you have, and what you can do is generate the smallest set of questions possible for the end user, in this case probably a doctor or a nurse, to run more tests to find out, thus getting down to the root cause as quickly as possible. So this doesn't work well in games, because in games we have all the knowledge that we could possibly want. The computer AI is built into the system. They can see what the player is doing. They have as much expert knowledge as they could possibly require, and nothing is hidden to them. So, as this applies to game, let's talk about a sample rule set. So in the game Rise of Nations, they have some simple rules about what it is to be fun. Based on the current difficulty level, they have a rule for how aggressive an attack the AI should take. There's also a rule about if a certain number of tanks attack, it will correspond to a certain aggressiveness. So, for instance, if 2 tanks attack, it's a mild attack. A mild attack is fun for an easy difficulty level. So therefore, if the difficulty is set to easy, the AI should attack with 2 units. Pretty simple. So in this case, difficulty is medium, then build 4 tanks and attack. So very simple. It's a little bit simpler than the initial rule set, so as to just make it quicker for the inference engine to actually get to the actions that it needs to take. In addition to rules, we can also build in data-driven systems. So rather than having hundreds of rules to determine what the build order of our structure should be, or what the location of these structures should be relative to each other, we can have a designer go ahead and basically create in this case, the structure location. So for Command and Conquer generals, the designer went in and built the base the way he saw it as being the best way to do this. Rather than generate rules off that, you just have the AI duplicate it every single time it plays. No longer need rules about that. You can focus on using the rules to drive the attacks. This is a really simple data structure, saves a lot of time. It's actually easier for the designer to implement rather than having to describe all these rules into a programming structure. You can just go ahead and list this out. Basically come up with relative coordinates. Okay, build the main building here, 2 units to the right, build the first factory, build some defensive structures relative to those buildings, so on and so forth. Another way of using a data-driven system would be to actually specify the order of creation. So rather than just setting up the base exactly as you want, you could say, okay, first things you want to do is build your main building. Second thing is build your first factory. Third thing is build a defensive unit. And let the AI kind of sort out where exactly it would want to build all of these things. Once again, a lot easier than building a rule, whereas the rule would say, if building 1 is created and you have resources for building 2, build building 2. If building 2 is built and you have the resources for building 3, build building 3. It's a lot of work. It doesn't really need to be stated over in the rule set. It's a lot easier to just abstract it into a data file where it's very clear what the order is. And the example the book gives is the Emperor Battle for Doom. So in summary, we talked about the 3 different pieces that make up an expert system, define what an expert system is and how it's used. We talked about how you can capture high-level knowledge and some of the problems that you might run into. Talked about the power of expert systems in order to quickly drive the actions that the AI should be taking, or outside of games, coming up with the best questions to ask so as to get to the quickest answer possible. We talked about how expert systems are embedded in games and how combining a rule-based system, so basically a knowledge-based, with a data-driven system, text files that are built by designers, works really well in games. And that is the lecture.